Continuing on, already we studied orifices and mouthpieces. They are used to find out discharge from a tank. And today, based upon those studies, we have to study time of emptying a tank through an orifice. Assume this is a tank, it's a cross-sectional view. This is a tank, overhead tank. And this tank is filled with water and it is provided with the orifice at the bottom, and through this orifice water will flow. See, this is the initial level of water. Say it is H1, initial head, and this is the final head. So after flowing water through this orifice, the water level will become from H1 to H2. Okay. So during this process, we can see that the tank is going to empty. Okay. So here we have to find out the time for emptying this tank. A small level we are considering DH. That is, this DH level of water decreases. And this level is at a distance h from this one. So this DH height reduction, what will be the time taken? That time will be integrated for H1 to H2 in order to find out the time taken for emptying this tank. So consider this tank having an orifice at bottom. A is the area of tank, small a area of the orifice, and H1 is the initial height of the liquid, H2 the final height of the liquid, and T is the time in second for the liquid to fall from H1 to H2. That at any time the height of liquid from the orifice is H, I already explained, and let the liquid surface fall by a small height dH at a time dt. Okay. So once again, so we are having this is the initial head, this is the final head, and during this traverse, the level of water decreasing to say then dH. So for that decrease, the time taken will be dt. Then the volume of liquid leaving the tank in time dt, as usual, it is A into dH. A into dH. A is the area of cross section. dH is the height of water. Decreases. Okay, therefore this will be the volume. And also we know the theoretical velocity V is equal to root 2gh. Already we studied. So the discharge through the orifice dq is equal to, what is that? That is, we are having, this is the velocity and this is the area. So A into V is the discharge. If you are multiplying with that CD, we will get the discharge through the orifice. Okay, this is for dq. So for dt time, the discharge will be CD into A root 2gh into dt. Okay. So this will be equivalent to our actual discharge. That will be equal to CD into A into root 2gh. As the volume of liquid leaving the tank is equal to the volume of liquid flowing through the orifice in time dt, then we have A into minus dH because it is falling. So A into minus dH, that volume will be is equal to, this is our theoretical. Okay, A into root 2gh, that multiplied with this CD into dt. So this V by T will be is equal to this CD into A root 2gh. Okay. So from that expression, this dt is equal to A into minus dH divided by CD into A root 2gh. And manipulating that equation, and you will get that A into H raised to minus half into minus dH divided by CD into A root 2g. That is H we have taken in the upper side. Therefore, it is simply root 2g. So by integrating the equation between H1 and H2, the total time T is obtained by, that is 0 to T dt, that is H1 to H2, that quantity we have to integrate. And finally, you will get 2A into root H1 minus H2 divided by CD into A into root 2g, where this small a is the area of the orifice, CD is the coefficient of discharge, H1 is the initial head, S2 is the final height. Okay. Suppose for emptying the tank completely, this S2 level will be equal to 0. So in the above equation, this will be 0. Therefore, we are having T is equal to 2A root H1 divided by CDA root 2G. So this is the time taken for emptying a tank from a height H1.